Start our next section today. So we've been exploring motion primarily in 1D, looking at energy and stability and so on. We want to, of course, ultimately be able to describe motion in higher dimension, in 3 dimensions, but it's actually, as we'll find, quite useful to think about 2-dimensional motion because there are lots of problems that are embedded in 3-dimensional space where nevertheless the motion is constrained to be 2D. So let's think about 2D motion, and if I have planar motion, of course we could just introduce with an x dot a y dot as well. We saw an example like that, but it's going to be more useful for us to think about polar coordinates. So let's let that be I and j, x and y axis, and take a particle, say, located here with radius r and angle theta with the x-axis. Then to describe the motion in polar coordinates, what I need is a basis vector in a radial direction and a basis vector pointing in the increasing angle direction, er and e theta. And I think do this in the geometry course, but let's repeat it here. So our polar coordinates relate to Cartesian coordinates via x is r cos theta, y is r sine theta, and our polar basis er e theta is defined by er is the vector cosine theta sine theta. All right, let's write it cos theta I plus sine theta j, and e theta is minus sine cosine. Okay. Right, so again, that's the vector that points in the direction of increasing radius, and that's the vector that points in the direction of increasing angle theta. So if I have a position vector, r as xi plus yj in this polar representation, that same vector is just scalar r er. Right? It's an er. In other words, I move in the radial direction by the radius. Right, so now I want to think about writing Newton's second law in this coordinate system. So let's express vector r dot dot in this polars. And the key to doing this is to make the observation. Of course, if I want to write x dot r dot dot here, it's very straightforward. I just get an x dot dot I and a y dot dot j. But if I'm doing 2 dots over here, I have to be careful because er changes with position, so which means the ddt's don't just affect that, but they also affect the basis vector. And so the key to doing this is to think about er dot, and to make sense of er dot, you have to think that in this definition here, theta is theta of t. Okay? So the key is that theta is theta of t, which means that if I take a ddt of er dot, that cosine turns into a minus sine theta times theta dot. And then the sine turns into a cosine theta, theta dot. But then we observe that that's the same as e theta times this extra factor of theta dot. So er dot is theta dot e theta. And if I do the same thing, take a d dt of the e theta equation there, you see I get a minus cosine theta theta dot I minus a sine theta theta dot j, which is exactly minus er times an extra theta dot. So e theta dot is minus theta dot er. And that's what we need to use. So therefore, let's work our way up to r dot dot. If I take just an r dot, and by the way, if you're occasionally a bit lazy about using something to denote vectors, you definitely don't want to be lazy here because we're going to have quite a few r vectors and r scalars. So we really want to be clear. Vector versus scalar. So if I take r dot vector, I get r dot er. And then by this boxed equation, I also get a plus r theta dot e theta. And even just before we go to second derivative, we just pause on that equation for a moment. We might, for instance, compare two kinds of motion. So one motion where only that term is present, and what is a different motion where only that term is present. And so that would look like in motion 1, if my particle is moving entirely radially. So let's try it this way. So theta dot is 0. That's radial motion. Or, on the other hand, put it here. If the radius isn't changing at all, that's circular motion, right? So that's little r dot equals 0. And notice, what is the velocity in each of these cases? The velocity, or the speed if you want, the magnitude of r dot, in this case is just the magnitude of little r dot, the scalar, how quickly I'm moving in the radial direction. In this case, you might naively say the velocity is theta dot, but that's not right. The velocity in this case is the magnitude of this, which is r theta dot. Right? You need the extra, whatever the fixed radius is. And if we were thinking dimensionally, that would be very clear because I need a velocity, which is the length per time, and theta dot does not have a length. Theta dot is a 1 over time, which is why you need the extra length showing up there. Okay. Okay, so that's velocity. And then if we want to take a second derivative, we follow the same script. We just have to be careful about product rule on these various terms. So r dot dot is, I get an r, scalar r dot dot er. I get an r dot, and then the er dot becomes an r dot theta dot e theta. Then I take, you see I get another one of those, take derivative on the first term over there. It's another r dot theta dot e theta plus an r theta dot dot e theta, and then finally the e theta dot gives me back an er, so that becomes minus r theta dot squared er. Or collecting those into the two basis vectors, we have r dot dot minus r theta dot squared er, and then the e theta has two r dot theta dots and an r theta dot dot. Okay. So polar coordinates, Newton's second law looks a bit messier. There's a really important sort of trick, which is that those two terms are actually collapsed into a single derivative, which is a bit hard to see, but you got a derivative on the r and a theta dot, and the derivative on the theta dot and just the r, so it sort of looks a bit like a product rule. And that, in fact, is d dt of r squared theta dot times 1/2. Which you can sort of check by going, no, that's not right. I need the 2 to stay there. This is a 1 over r d dt of r squared theta dots. You can expand that and see that that works. That's going to end up being kind of key to much of our development, is that the angular component of Newton's law, second law, collapses to a derivative of a quantity. Okay? So this is, put a star, something next to that. This is going to be a very important trick for us. So therefore, just have one nice equation that we can put a box around. R dot dots is r dot dots minus r theta dot squared er plus 1 over r d dt of r squared theta dot e theta. I would say ultimately we're going to be using this a lot, and you might benefit from just memorizing it, but this derivation you should also be able to do when needed and without too much time. Okay. Let's think about the acceleration, so this is r dot dot, in the case of motion 2. So in the case of motion 1, it's quite straightforward. The second term drops, that term drops, we just get r dot dot. In motion 2, our circular motion, so in that motion, we're saying that scalar r dot is 0, so that scalar r is some constant, which we call capital R, is fixed. And if we make it even more simple, suppose that theta dot is also a constant. We'll call that constant omega. Then that's a constant times a constant, so d dt of that is 0, which means that r dot dot is just minus r. Right, so this whole term drops out, that term drops out, and we're left with just this term in r dot dot. So r dot dot is minus capital R theta dot, which we're calling omega, squared er. And recall that v, the velocity for that circular motion, is actually, let's define the speed, the magnitude of r dot, which is r omega. So therefore, r dot dot is minus v squared over capital R er. What is that saying? Saying if I'm moving around in a circle at constant constant change in angle with a fixed radius, my acceleration is pointing inward and is equal to, has a magnitude, the velocity, my speed squared over radius. Okay? Or angular velocity squared times the radius. Okay. Notice I'm not talking about forces here. This is just computing the acceleration. The force you feel, if you're, say, in a car that's driving around in a circle, the force you feel is outward, and we'll come to that later in the course. This is just your acceleration is pointing inward. Okay, let's go to conservation of energy. Actually, we don't need to do this in 2D. We can do this in 3D, higher if you really wanted to. So this is going to very much mirror what we did in 1D, so let's just quickly remind ourselves. In 1D, we have m scalar x dot dot is f of x, and f being a function just of x is a conservative force. If we define v prime as minus f, then we get to the equation 1/2 mx dot squared plus v is E constant, potential, kinetic plus potential is constant. Yeah. No, please.
That r dot dot there, should it be a vector? Like after like constant. So.
Oh, so you just have to.
Really
yeah. See, after I'm saying how important it is to be careful with marking things, yes, that's vector. Thank you. Do stop me when I make mistakes. Okay. Anything else? So that's what we've done in 1D. In 3D, it's going to look very much the same. So if I have m vector x, I want to do it that way. Let's do vector r, because that's what we're doing over here. So what's the equivalent? Conservative force there. I had an antiderivative. In 3D, f is a vector field. To be conservative, we need an antiderivative, which means there's a v such that the gradient of v gives us f. So if f is minus grad v, so in other words, minus v dv dx, dv dy, dv dz, then we say f is conservative. You've probably been doing similar thing in the multivariable calculus course. And then I make the same kind of steps there. If I take Newton's second law in this form, now I imagine dotting both sides of the equation with r dot. And m r dot 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 r dot is d dt of m r dot squared with a 1/2. And f dot r dot, which is minus grad v dot in r dot, is d dt of v. So what we get is m r dot dot r dot dot, which is 1/2 d dt of m r dot squared. In other words, magnitude r dot dot r dot. If you unravel that derivative, you get r dot dot r dot dot. Dots going on, and equals minus grad v dot r dot, and grad v dot r dot is d dt minus d dt of v of r. And that one's maybe a little harder to see, but again, if you go the other way, take a d dt of v. V is a function of r, x of t, y of t, z of t. Chain rule is going to give you a grad v times an r dot. Okay. So therefore, my conservation of energy is that 1/2 m magnitude of r dot squared plus v of r is constant. Which again has the exact same form. Kinetic energy plus a potential energy is constant. Total energy. We can also extend these ideas of work. So before in 1D, we said that the work done is the force times the distance. The W was an integral of f of s ds as s goes from whatever point x1 to x2. The 3D version of that is I integrate my vector field f along a line. So f dot dr over some curve. So I have some curve C, and that's the path r of t, right? So the object, our particle, is following this path through space. Now let's suppose at this point it's at, call that time 1 and time 2. This looks the same. This is the same as this if I chop this line into lots of little small one-dimensional motions, right? So it's a line integral f dot dr. And well, what we can do with that is that's an integral of f dot dr dt dt as t goes from whatever, t1 to t2. But f is m r dot dot by Newton. So I have an m r dot 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 r dot, but that's 1/2 d dt of m r dot squared, the same thing we just did above. Right? So this is m over 2 integral d dt of r dot squared dt, which is just the antiderivative of the derivative, which means I just get r dot squared times m over 2 at the endpoints. But that's exactly the kinetic energy at t2 minus t1. So if we go back here, that's t. So it's the same result we had in 1D. The work done in moving this particle under this force field is the change in kinetic energy from the end time to the beginning time. And then we can also make this connection with the potential energy. So if energy is conserved, then t of t2 minus t of t1 is just v of whatever position that is, r1 minus, opposite, v of r, t, this way, t of t1 plus v of R1, I'm going to call R1 the point corresponding to where the particle is at time t1, equals t of t2 plus v at position R2. So therefore, t of t2 minus t of t1 is v of r1 minus v of r2. So therefore, w is v of r1 minus v of r2. It's the same statement we had before. The work done is the difference in kinetic energy, but that's the same as the difference in potential energy. And it's flipped because if I'm raising an object, the potential energy is going up, the kinetic energy is going the other way. And the other important observation about this is that quantity only depends on the endpoints. Right? Only depends on the endpoints, but we started with a path integral, right? Integral f dot dr. If it only depends on the endpoints, then that path integral is path independent. Okay. Right. Let's think about some specific potential energies. So if I take the easiest example would be gravitational field close to Earth. So if I take gravity F is minus mg k, which is pointing down. I'm looking for, this one's easy because I've written in Cartesian. In Cartesian coordinates, we just take the antiderivative in each component. V is just mgz. It's the same thing as the 1D version we had before. I'm just now using an actual vector for F. And again, the sign there reflecting that the larger the value of Z, the higher the potential energy. So that's not super interesting. What will be more interesting for us, and we'll spend a lot of time developing, is what's called a central force. So F, vector F, is called a central force. If F is proportional, so that's a slightly ugly version, that's a proportional symbol. If F is proportional to R, the position vector. And I'm not talking 2D here, I'm talking generic, 3D at least, though this works in higher if you wanted. So F is proportional to the position vector. So R is the position vector. And just so we don't forget, because at some points we will relax this, I mean a position vector in an inertial frame. Sort of our default is to think of inertial frames, but good to remind ourselves once in a while, because by the end of the course we'll think about the frame being non-inertial, which means the frame itself is accelerating. So we're thinking about a non-accelerating frame as a force that's pointing either with or the opposite direction of the position itself. So there's R, and we're saying F is pointing along that line. Yeah? So the claim that we'll aim to show is that if I have a central force, then the motion, this is in 3D force, the motion is constrained to be 2D. The motion lives in a plane, which is why this plane formulation is going to be useful. Okay? And central force is incredibly important because gravitational force away from the approximation near, say, the Earth's surface is a central force. Right? The Earth is being pulled towards the sun, towards the force that the sun applies to the Earth is a central force, okay? And many other forces. So we can talk about the potential energy for such a force. So if F is a function of that's a particular central force, the kind of one we'll mostly think about. F is a scalar function of the radius and pointing in the direction ER, or I'm now thinking a three-dimensional ER, which is just the position vector normalized. Okay? So my claim is that since I have a scalar here, my vector is defined via this scalar function of the position. The claim is that I get a potential energy by finding the antiderivative, minus antiderivative of that scalar function. And so the claim is that F is minus grad V, where V prime is minus scalar F. So let's check that. If I'm in Cartesian coordinates, then R is, say, x, y, z, and magnitude R is root x squared plus y squared plus z squared. And let's go the other way. So I'm going to suppose that V prime of R is minus F and show that grad V gives me minus vector F. Okay? So, well, in grad V, it's of course a dV dx. So if we just think about dV dx, that's dV dr, V is a function of R, dr dx. dV dr is V prime, which is minus f of r. In fact, that's not even a partial derivative. That's like that. dV dr dx, so that's minus f prime, sorry, minus f of r, the dV dr. And dr dx, sorry, this is scalar r is the magnitude of vector r, yeah? So if I take a d dx of that, I'm going to get a 1/2, this whole thing to the negative 1/2 times a 2x, so the 2 and the 1/2 cancel, which means I'm left with an x over this square root, which that's an x over r itself. You see that? So, therefore, grad V, I'm going to get the same thing with the dV dy y over r times f and so on, which means that grad V, or minus grad V, is f of r times x, y, z over r. But this is ER, right? That's position vector over its magnitude. Which is vector F. Okay? So that's a particular kind of central force where I have a scalar function of radius, and the statement is that the potential energy, I just need the antiderivative of that scalar function. Okay. Right, so as I said, my claim is that for a central force, the motion is actually living in a plane. And to get to that statement, we need another concept, which is angular momentum. We also need this concept more generally. So far, Newton's second law is really a statement about a balance of linear momentum. My linear momentum, as we've defined on one of the first lectures, is the velocity vector of a particle times its mass. Right? That's the momentum that the object has going that way. So it's sort of linear momentum. To complete the picture of the dynamic motion of an actual physical object, I also need a momentum of rotation, and this is what we need here. Angular momentum. So the angular momentum of a particle let's give it mass m at position r of t. So from the outset here, this is kind of the starting point for the concept where things get a little less intuitive. So I want to be very careful we're understanding at the beginning. Angular momentum, we're talking about things like rotating. And it only makes sense to talk about a momentum of rotation if you also include what the thing is rotating about. I can't just talk about rotation as a generic concept. I can only talk about rotation about a point. Okay? So anytime we introduce the ideas of angular momentum, we should also then be thinking about what. So in this definition, I'm going to say the angular momentum about, let's call it point P. And let's suppose that point P is located at position x. And in fact, that could be x of t. Is, okay, let's write the formula and then make some sense of it. So we'll use capital L for angular momentum. It's a vector. The sub p means about point P. And we take the vector r minus x cross m r dots. So notice this vector here is the linear momentum, right? Mass times the velocity. And this vector here is the vector that points from the point P, where I'm measuring rotation about, to the position of the particle. Okay, so my picture is, I have an origin, I have, say, here's my particle, r of t. Here's, say, point P, so this is the vector x. And this particle is moving, so it has a velocity, and let's make its velocity, say, pointing like that. In fact, we'll give it, that's its linear momentum, mr dot. And so what we're doing is taking this vector r minus x cross that one. Okay. So note r dot is the velocity in an inertial frame. We need to say that again. And in particular, when we get later to the course, this is going to be really important to keep in mind. Relative to an inertial frame. So what is LP measuring? What we can think of as an instantaneous rotation about P. Instantaneous rotation and the way to think intuitively about that is think about the two situations that would cause LP in magnitude to be largest and when it would be smallest. Right? So compare. How do I make LP 0? Well, there's a couple ways I can make it 0. Either I have no momentum at all, r dot is 0. That's a bit boring. No linear momentum, there's no angular momentum. If r dot is non-zero, how do I get this thing to be 0? Well, I need the cross product to be 0, and the cross product is 0 if those two vectors are aligned, parallel. Right? So if r minus x points in the same direction as r dot. So r minus x is parallel to r dot. So what does that mean? So here's x, here's r minus x. If I extend that to an entire line, then we're saying if the velocity, if the particle is moving at that moment, right, when it's at that point r, if it's moving in a velocity that direction, then LP is 0. And why are we saying that? Well, in that sense, there is no rotation. The particle is not in any way rotating about x. It's sort of moving directly away from x or moving directly towards x. There's no rotation about x. Okay. On the other hand, how do I make that vector maximum? So suppose I fix the magnitude of r dot. LP is maximum when the cross product is maximum, and the cross product has a magnitude that depends on the sign of the angle between the two vectors. So it's maximum when the two vectors are orthogonal. Yeah. So maximum when r dot is perpendicular to r minus x. In particular, if we go back to sort of these pictures we had over here, circular motion, right? Compare case 1 and case 2. If I let x, my point P, be the origin, so x is the 0 vector, what we can do is compare, we said radial motion in radial motion, r dot is alpha r. right? The velocity is just going outward or inward. And LP is exactly, L0 is 0. It's really just repeating what I've said here, where I take x to be the origin. If the particle over here, x equals 0, means I'm measuring rotation of the particle around the origin. If it's just moving radially, it's not rotating in any sense, LP is 0. Sorry, L0 is 0. Whereas for circular motion, that's where I have r is some fixed radius ER, and theta dot is omega, then L0. So as we said, r dot is r theta dot E theta, which means that L0 is r cross mr dot gives me an r er cross m r theta dot E theta. Okay, we didn't do it over on the left, but I was using ERs and E thetas for 2D, but I can extend that to cylindrical coordinates by adding an EZ, and it's easy enough to check that ER cross E theta is EZ. So here my cross product is between ER and E theta, which means my angular momentum, L0, is m r squared theta dot EZ. And the key point is that in that motion, in circular motion, r dot is perpendicular to r at every instant. Which means for this particle that's just going around in a circle, its angular momentum about the origin is maximum for given rate of velocity, which fits our intuition. That is, the maximum rotation I can have is to go in a circle, right? And then everything else is in between, going at radial line or going in a circle. Okay, so now comes the big claim. It's a two-part claim. One, for F, a central force, a particle satisfying Newton's second law for this F. So in other words, a particle satisfying m r dot dot equals F will have constant angular momentum L0, or will also satisfy L So I'm going to use, we'll think about the origin, and sort of by default, if we don't put the subscript, we probably mean sub-0. So that statement, if I am acted on by a central force, then my angular momentum about the origin, where the central force is pointing, is constant in time, okay, unvarying. And the follow-on, statement 2, is that the particle's motion is constrained to a plane. It's quite an important result, since I have a three-dimensional space. I have a force that's acting in 3 dimensions, but if it's a central force, then the motion is actually a 2-dimensional motion. I just need to figure out what that plane is, and then I'm back to 2D. So I think we have time to at least prove statement 1, and maybe we'll pick up next time with statement 2. So the proof of 1 is straightforward. I'm claiming that L0 is constant, so that means that d dt of L0 I'm claiming is 0. So if I take d dt of L0, that's d dt of r cross m r dot, which is an r dot cross m r dot, which is 0 because I'm crossing something with itself, plus an r cross m r dot dot when the dot derivative goes to the second term. But mr dot dot, that's Newton's second law, is equal to F. So this is R cross F by Newton. So if F is a central force, then it points in the same direction as the position vector R, which means this is also 0. So L0 dot is 0, which means L0 is constant. Okay, let's stop there, and we'll pick up with statement 2, start next time. Okay, so that's a quick summary of what we did last time. So we started thinking about motion in 2D in polar coordinates and derived this form of the acceleration. And we started thinking about central force. Central force is the force is in the direction of the position vector. So the force is always pushing towards the origin or away. And defined the concept of angular momentum. So that's about point P. P is located at position vector x, and we take the difference r minus x cross with linear momentum m r dot. And then at the end, we made this claim that if F is a central force acting on our particle at position r, then the angular momentum about the origin is constant. We showed that at the end. And then the follow-up, which we'll start by showing now, is that, and this is quite an important one, the motion for central force is therefore restricted to a plane. So let's prove this second statement. And it's really, we want to use the first statement. So the angular momentum, L0, is constant. So let's suppose for the moment L is constant but not itself the 0 vector. So L, I'm using L for L0, so x is the 0 vector. So L, by definition, is r cross m r dot. And the key is that that's a cross product. Cross product is orthogonal to each of the two input vectors, which means that this constant vector L is orthogonal to both r and r dot. Right? So L is dot r is 0, and that's the same as L dot r dot, which means that there's a single vector. I can define a plane that has L, this constant vector, as its normal vector, and r dot at all times are living in that plane. Right? All times in the fixed plane which has normal vector L constant. But r is the position vector itself, and r dot is its velocity. So therefore, the particle never leaves that plane. Right? So that means its motion is that in that plane. So that's assuming that L was not itself the zero vector. Actually, if L is the zero vector, that's a sort of easier case. Right? If L constant is the zero vector, then it must be that one of the input, well, okay, two possibilities. Either R is 0 or R dot is 0, which means nothing's actually happening, right? Or R, which still means it's restricted to a plane because it's not moving at all. Or R is parallel to R dot. There's no motion. But if R is parallel to R dot, then what is the particle doing? Take that radial line, and it's just following that radial line, which means it's moving actually in a line, and a line is a subset of a plane. Restricted, run out of room, restricted to a line. Okay? So the consequence is actually quite impactful here. What we'll do in a few weeks is think about planetary motion. Planets, to a pretty good approximation, are acted on by a central force, the central force of gravity. That's a central force. And the consequence from this is that the motion of a planet is therefore restricted to a plane. Okay? So we'll come back to that. Try to work out that path of motion. But we'll come back to that in a couple weeks. Let's say a little bit more about this. So, well, I can work out that constant. It's constant for all time. So take any time point, I plug it in and work out the L, and that's what I get for all time. L0 can be determined so in other words, I guess the easiest thing to imagine is you give me the initial position and the initial velocity of the particle under a central force. I work out the L. That's going to tell me the plane of motion. Right? Without loss of generality, if we want to connect to the upper bit of the board where we're doing planar polar coordinates, without loss of generality, I can choose L0 to be aligned with K. Z-axis, which means that I can describe the motion as we've done above, R equals R ER. So that's K. My particle's moving in the XY plane, if you want, described in terms of radius and angle. And let's compute L0. So L0 is R, which is RER, cross R dot, remember, has two components, got an R dot ER and an R theta dot E theta. And do that times m. And ER cross ER is 0. ER cross E theta is EZ. So I'm left with R squared theta dot EZ. Notice we didn't talk much about this the other day. So we talked about angular momentum only is defined about something. And what the output is not a scalar but a vector. And the way to interpret the vector is that at any given point in time, an object that's rotating actually has an axis of rotation. Say, imagine a tiny little time increment. The particle's tracing out a tiny arc of a circle, and that's like going around the circle that defines a plane. So the way to interpret angular momentum is it's a vector whose direction is the axis of rotation and whose magnitude is how quickly you're rotating at that instant in time about that axis. Yeah? So L0 here, we see EZ, which is K, is the axis of rotation. We already knew that from the setup because we picked K that way. And we see that R squared theta dot is sort of telling us how quickly the particle is rotating around the Z axis, which you can kind of see from the theta dot, right? If theta dot's 0, it's not rotating at all. But the other consequence from this is that I said L0 is constant, which means that R squared theta dot itself must be constant. So therefore, for a central force, the angular momentum okay, I'm repeating myself there. Angular momentum is constant, is conserved, but moreover, R squared theta dot is constant. And we're going to make lots of use of that fact in the coming lectures. R squared theta dot, we're going to call that H, and that is also constant. Actually, we could have come to that conclusion via Newton, via a different route. If you go back and write down Newton's second law in this polar coordinate system, I get m r dot dot, and r dot dot had r scalar r dot dot minus r theta dot squared er plus, as we said, the nice way to write that is with the 1 over r d dt of r squared theta dot e theta equals F. And central force means that F is itself radial. But that means there's nothing balancing on the right-hand side the angular component of the acceleration. So this must be 0 for a central force, and since we've written it this way as a d dt, this thing must be constant. So we conclude. Same again. Okay, different route to see the same thing. Okay, we will have, as I say, lots to do with that boxed equation, but I want to talk about torque first. Definition. We'll use the symbol tau for torque. Tau p, the the torque of a force same with angular momentum. Torque only makes sense to talk about something. So the torque of a force F about point P with position vector x acting on our particle at r of t has a quite similar definition to angular momentum. Tau p is r minus x cross F. And we'll make a little note that this is also sometimes referred to as the moment of F about P. Oops. We'll try to stick with the word torque. Okay, so to make some sense of that, the easiest thing to think about is tightening a bolt. Right? So consider a spanner, or what I would call a wrench, which is, okay, let's try a little picture here. So I've got a bolt going into the board. I take my spanner, I want to tighten it or loosen it, and looks something like this. Grabs on. Yeah. What do? You apply a force here, that way, if you want to maximize your efficiency. And what you're doing is applying a torque about this point. So that's like my x. I'm applying my force there. And I'm getting a rotation, ideally, of r about that point. Yeah. So the way, the terminology I always had learning these things was, we called that the lever arm. And if you ever try to loosen a bolt without a lever arm, you're going to find it's very, very hard. That's why we can't do it with our fingers. But if you give me some distance here and apply the force there, I get a torque. Yeah. And indeed, the tighter the bolt, kind of intuition says, and if you ever tried to like loosen the bolt on a tire, it can get very tight. The longer the lever arm, the more torque you produce. Right? I need my r. This is my r minus x. Has the same shape, has the same form, r minus x cross f. So that's a vector whose axis, who's pointing this way. Right? Right-hand rule. Actually, it's pointing that way into the board. Means I'm getting a rotation that way. If you think about the units of torque, so it's a length it's a length times a force, right? Which is the same as a length times, that's a mass times a length per time squared. So it's a mass times a length squared per time squared. And We won't do much more with this right now, but this idea is going to be critical when we come to think about motions of rigid bodies later, a bit later in the course. As I said at the very beginning, what I want to do is I want to understand the motion of a pen that I toss in the air. And up to now, the pen hasn't really been an object, it's been a point mass, right? But a pen really has an orientation and it's rotating as well as translating. And Newton's second law is not sufficient to describe both the motion and the rotation. Newton's second law is really just going to give us the motion of the center of mass, as we'll see. So I need to extend Newton's second law to also describe rotation. And the idea let's write this as a claim, is that a balance we need to do is extend Newton's second law, which was a balance of linear momentum, to include a balance of angular momentum. And that equation in my claim has the form the time rate of change of the angular momentum is the torque, tau p. And that's, again, just to be careful, that's if p is in an inertial frame. And just in terms of my comment I just made about the pen, that's a complication we'll have to figure out, because if I'm thinking about the pen rotating, that's not an inertial frame, right? The pen itself is accelerating. What we'll do is put a basis inside the pen. Be careful about that. Non-inertial frame. Okay, so my claim is that that's sort of the extension of Newton to rotations, and that's actually almost immediate consequence of Newton. So the proof of that equation there, we can simply take a derivative of LP, right? So ddt of LP is ddt of R minus X. Oops. Yeah, I guess that. Cross mr dot. And okay, so I said before X could move, but I'm also supposing that P is an inertial frame, and so I could that means that X, the position about which I'm measuring torques and moments, is allowed to move, but it's not allowed to accelerate. And if it's not allowed to accelerate, I can just move my coordinate system along with it. So I move my origin to follow that position, and then we take x dot equals 0. So when I take my derivative here, take x to be a constant. And therefore, what do I get in this derivative? I get an r dot cross m r dot, which is 0. And I get an r dot dot cross m r dot. So actually, yeah, so the r dot cross r dot goes away, and then I get an r cross m r dot dot. Sorry, r minus x cross m r dot dot. But m r dot dot is F, whatever force is acting on the particle. And you see I've gotten back exactly to the definition of tau. Okay. So this equation is almost immediate from the definition of angular momentum and the definition of torque plus Newton's second law. As I say, that complements Newton's second law, and as we'll see, that's going to describe rotations. It's worth doing a direct comparison. It's the balance of linear momentum which is our other name for the F equals ma, is m r dot dot equals F, but I could also write that equation as d dt of m r dot equals F. And that's a nice way to write it because mr dot, mass times the velocity, is what we call the linear momentum. So balance of linear momentum says any change of the linear momentum equals balanced by whatever forces are applied. Angular momentum, any change of the angular momentum is any torques. So they have the analogous form. Okay. And of course, that's assuming, as we've assumed all along, that the mass is not changing, but the equation is still valid if the mass did change. Right, we will do a lot more with that equation when we move to rigid objects, but what we're going to do first, this is section 5 of the notes, is look at what we'll call constrained systems. So we say a particle is constrained if its motion is restricted. To a subset of R3. So two common examples. You could have, imagine a ball or a particle rolling on a surface. So let's take a simple picture. I take a marble and I roll the marble around in a bowl. Right? So the motion of the marble is living only on the surface, in this case, the inside surface of the bowl. Right? Another example could be a sort of, they make for nice problems, is a bead on a wire. We saw an example like that the other day. And the constraint means that when I consider the motion, I'm only allowing the particle to ever be in that subset of R3. In this case, 2D subspace. In this case, it's on a wire, so a 1D subspace. Okay? Okay, so conceptually, a constrained motion reduces the dimensionality, right? The constraint reduces the dimensionality, 2D in that scenario, 1D in that scenario. But we have to be careful. We have to introduce a constraint force. Actually, generically, generically it introduces a force. I'm writing the force as n because I'm going to take that n to be normal. Generically, there's two components of a force. There's a force in the plane along the direction of the surface or the wire, which is like a friction force. And then there's a normal reaction force, as we've talked about before, which is perpendicular to that. So for the most part, we'll restrict we'll say mostly just in case we ever want to frictionless constraint forces. So for instance, if you're doing a problem and instead of setting it up, the kind of words you want to look for are a smooth surface, or sometimes we just say frictionless. So what that means is that if I think about that marble rolling around in the bowl, rolling along the bowl is not, there's no friction, there's nothing opposing the motion, but there's still a force there. And the way to think about the force is that the ball is pushing against the surface and the surface is pushing back. Right? That's our normal force, and it's always perpendicular to the constraint space. So N is perpendicular to the constraint space. And we've already had this terminology, but remind ourselves that's called, we call it the normal reaction force. Okay, so to give ourselves, to make this slightly more mathematical, let's define the constraint space as a space which we'll call capital U, and U is some subset of R3. So that's, in this picture, U is the surface of the bowl, and in this case, U is the curve of the wire. And what we're saying is that at any given time, I'm only considering a force that goes perpendicular to that space. Right, so one consequence of that statement, that N is perpendicular to the constraint space, is that N is therefore orthogonal to the tangent vector, the velocity vector of the particle. Right? By definition, R dot is in the set U. Right? My marble is rolling in the bowl. Its velocity vector points tangent to the surface U, which means that N dot R dot is 0. And that means that the work done by that force is also 0. Because the work done by the constraint force, W, so we've written is the integral along whatever path the particle is taking of the force, N dot dr, but that's N dot R dot, which is 0. So that means that the fact that the marble is sitting inside a bowl, the bowl is pushing on the marble, but it's not doing any work. And there's another consequence of it not doing any work, which is that I still have a conservation of energy. In fact, the conservation of energy is unchanged. And we can see that if I write down Newton's second law, mr dot dot is F. I'm going to break down forces into whatever force is separate from the constraint force. And let's suppose that's, I'm going to assume that's a conservative force, that I started with a conservation of energy, plus my normal reaction N, where F is minus grad V. And remember, how do I get from that equation to conservation of energy? I dot everything with an r dot. That becomes d dt of the kinetic energy. The grad V minus grad V becomes d dt of V, which I put on the other side. And I get a d dt of kinetic plus potential is whatever's left. And you'd think that could cause problems, but when I dot that with r dot, it's 0 by construction, which means that n dot r dot equals 0, which means that 1/2 m r dot squared plus v is E constant as before. Okay, so that's assuming frictionless. Just to kind of have a complete picture, let's think what would happen if I did have friction. So whichever friction model we have in mind, the key to friction is that it's opposing motion, right? So that's an extra force which is in the opposing direction of my travel, right? So whatever r dot is, I have some force. So that's like, let's call it F friction, F sub r, Fr is generically like that, this is some function, whatever you want, but it's in the direction of minus r dot, right? So if I go back to this statement, m r dot dot equals conservative force, and let me just go and immediately write that conservative force as the gradient of a potential, so minus grad V plus N plus this friction force what's going to happen? What happens differently? Let's do the same steps. Multiply that thing by r dot, put the V on the other side, the n dot r dot goes away, and our conservation of energy is no longer d dt equals 0. Right now it becomes d dt of 1/2 m r dot squared plus v equals this thing dot r dot, which is minus F friction with r dot squared. Okay, so pay attention to the sign there. What's the difference? And think about that marble. So in scenario 1, there's no friction. The bowl is very smooth. The marble is sort of rolling free. The normal force that the bowl is applying to the marble isn't doing anything to change its conservation of energy. But if the bowl is a little bit sticky, applying some resistance to the motion, This is like still my total energy, kinetic energy plus potential energy, and now it is negative, which means energy is decreasing, which is exactly what our intuition would say. Right? If I have friction in the system, energy is being lost. As we said a couple weeks ago, it's being lost because I'm heating up the bowl a tiny bit. Right? It was being lost to the particle. That's E. So d dt of E is negative. Okay. Mathematically, we don't like that. Makes our equations less pretty. So that's why, for the most part, we'll skip friction. Of course, it exists in basically all systems. I think it's a nice exercise to imagine a world where there is no friction. It's not actually a very nice world. You could get to class by just giving yourself a little push and then slide all the way till you're at class. But there'd be a downside, I'm sure. We want to be careful about signs here. And in particular, okay, so I'm going to ignore friction from now on, but I want to think about the sign of n, right? Which way should n point? So if you keep in mind intuitively, as I said, what is n? N, if I have something on a surface moving under gravity, that n is appearing because gravity is, the object is being pulled down, it's pushing on the surface, and the surface is pushing back. So we expect n to point up. But as a nice thought experiment, and in honor of the Olympics, let's imagine a snowboarder. Here's a slope and there's a hill, right? Snowboarder comes down. Let me draw somebody here. That's how they look. Comes down the hill, goes up this hill, and then they jump. Right? But let's say, what is the condition to jump? Depends on how fast you're going, right? Are you going to jump when you hit that hill, that jump or not? How can we make sense of that? So you think about this equation, m r dot dot is minus mg k plus n. So I can think of rearranging that. So my normal force is m r dot dot plus mgk. There are kind of two parts to the motion. When the snowboarder is going through this bit, obviously mgk is always pointing, so this is minus mgk. So mgk, there's a component pointing up, and then n has a component due to the acceleration. When I'm going through this bit, which way is that acceleration vector pointing? We did that on Monday. If I'm going around a circle, perfectly circular motion, from our calculations in polar coordinates, the acceleration points to the inside of the circle, right? So as the snowboarder's coming through here, let's imagine I approximate that as an arc of a circle, r dot dot is pointing up, or at least away from the surface. And mgk is also pointing away from the surface, so that means n is pointing that way. Yeah. Now I come up the hill and I start going over this bit. Same story, I've got a component pointing up, but now my circle is the other way around, is inverted, which means the acceleration is now pointing this way. So what does the snowboarder need to do if they actually want to lift off? They need that vector to be big enough that it cancels out that one. So depending on r dot dot, n might be pointing up or it might flip to point down. pointing away from the surface. What would it mean if n is pointing away from the surface? As I said, n is the force of the surface applying to you. I'm pushing against the surface, surface is pushing back against me. If suddenly I'm pushing against the ground, if suddenly that force flips directions, that's like I'm pulling away from the surface and the surface is pulling me back down. But the surface isn't doing that, right? Unless there's glue on the surface, it doesn't have that ability to pull you back down. So a flip in the sign of n signals that the snowboarder leaves the ground, right? So as long as n stays pointing up, we stay on the hill. If n flips sign to pointing down, still do the maths, but it no longer makes sense. The surface is grabbing you instead of pushing on you. You leave the ground. Okay? So you leave the surface if n, actually you leave the surface at the point n equals 0. But unless there's some property of the surface that can hold you to it, that's the condition for jumping. Okay, I want to do, at least get started with one more example. And we're going to consider, let's do it here. A pendulum, a simple pendulum. What we mean by simple pendulum is that I have a mass sitting down here, and it's attached to the origin by some string or rod of length L. But the rod, we're going to suppose, has negligible mass. Okay. And let me set up my coordinates. So I'm going to call that, this is gravity is pointing down, so gravity is acting in the minus z direction. And I'm going to define angle theta as the angle slightly different from normal, as the angle between the negative z-axis and the position of the particle. So, in the language we've been using over here, the constraint space is this circle of radius L. And that's in the xz plane as I've drawn it. The constraint force so one way to do it is, I've said the constraint force is perpendicular to the constraint space, and perpendicular to the circle is the radial direction. I'm going to write the constraint force as, so that's the ER direction. If I make ER my radial vector, and I'm going to put a minus t there, and that's motivated by the physical meaning of that constraint force, which is that it's holding that pendulum at a fixed radius. So you can think of it as gravity is pulling the object down. That means that the object is pulling on this rod, pulling it away, and the rod is pulling it back because it's not letting it leave that radius. So I'm putting it as a minus TR. So that T is the tension in the rod. t is greater than 0, so long as the object is being held from being pulled further down. Okay. So, yeah, I mean, the point is I'm not allowing the length to change. Let's see if we can set up the mechanics or the dynamics of this system. So I need to start with a bit of geometry. So our position vector has fixed radius L, acting in the ER direction. And note that ER, if I convert that to the x and the z components, ER has a, let's see, sine theta I minus cosine theta k. E theta, perpendicular to that, is a cosine theta I plus sine theta k. I can take r dot is L theta dot E theta, r dot dot is minus L theta dot squared ER plus L theta dot dot E theta. So Newton's second law is going to say that m times minus L theta dot squared ER plus L theta dot dot E theta, acceleration, equals two forces. So I have gravity minus mg k, and I have my tension, which is minus T ER. That's a slightly funny looking equation because I've got terms on the right that have different basis than the terms on the left. That's fine. I just have to be careful how I combine them. And then a key point is that I don't know T. Right? T is whatever the rod has to do in order to keep that particle at that fixed length radius. So if I take this equation and dot with ER, then I have to be careful because I need to work out what K dot ER is, but I've got ER written that way, so K dot ER gives me a cosine, so I get M minus L M theta dot squared is minus mg times minus cosine theta, because that's K dot R, K dot ER, minus T. And if I dot with E theta, I get ML theta dot dot is minus mgk dot E theta, which is sine theta, minus mg. Okay. So we'll pick this up next time, but just looking at that, I have two equations, right? But really just this single variable, theta. If you tell me theta of t, I know the motion. So the way to think about that is the second equation I can just solve for theta. That gives me the motion of the pendulum. And once I know theta of t, I can put that into the first equation and work out what the tension is in the rod. And there's a nice exercise you can do, which we'll do in a problem sheet, which is if I'm on a swing at a playground, you can do the same thing. And then the question is, what happens if t flips sine? So up there, n flips sine is great for the snowboarder. That's what I need to leave. What happens if t flips sine in a pendulum? I'll let you think about that on problem sheet. Okay, let's stop.